All right, so this next section that we're going to talk about is section 5.3, and we're going to be talking about points on circles using some new functions called sine and cosine. All right, so again, we always go back to drawing our Cartesian coordinate plane. And I'm going to, again, attempt to draw a circle that's centered at the origin. And we've seen so far that we can describe points on a circle using an angle right here or a distance. But an important application of trigonometry is also to relate those points to our XY coordinates. Okay, so what I'm going to do is just say, here's one circle here, and I'm going to call this R1. Okay, and if I wanted to talk about the points on this circle, I can call them X1 comma Y1. Okay, I can draw this line down right here, and I know that this is my X1 value and this is my Y1 value, the vertical distance. Now, I can draw a circle. Again, let's pretend it's centered at the same place, bigger radius. And now notice I'm going to have the same angle. My angle is not changing, but now I obviously have a bigger radius called R2, and this distance is X2, Y2. So my corresponding point on my first circle with the radius R1 is X1, Y1. Okay, same angle, bigger radius. Notice it's X2, R2. Well, what we can essentially do for both of these guys is draw a line down, okay, to form right triangles. So essentially what I have is as follows. Same angle, but I can say that this is Y2 and X2, and this whole distance is R2. And then I have R1 right here, and this distance is X1, and this is Y1. Okay. So notice I have a right triangles. Okay. Same angle theta. I'm just kind of enlarging this little portion right here. Well, these are similar triangles. In other words, they're the same angles here. This is the same, and therefore this angle and this angle are the same. Okay. We know that similar triangles have the same angles, and so their corresponding sides are proportional. Okay. In other words, the ratios are constant. So for example, I could say that Y1 is to R1 as Y2 is to R2. And similarly, not only can I talk about that in terms of my Y values, but I could say that X1 is to R1 as X2 is to R2. These ratios, in other words, the ratio of my Y value to my radius, as well as my X value to my radius, they're going to be constant for any given angle. Therefore, these ratios only depend upon the angle. So what we want to do is we want to say, well, because these ratios are constant for any given angle, let's define the ratio of the sides as a function of the angle. Okay, so what we say is for an ordered pair XY on a circle with some particular radius R and angle theta. Okay, again, these things are completely defined by my angle. we say that our sine function, so we write sine of theta, is going to be the ratio of y over r. And our cosine function, which we write as cos theta, is the ratio of x over r. Okay, this is how we define these functions. And again, it does not matter what our radius is, because these ratios are going to be constant no matter what. Okay, so these are functions that are totally dependent upon our angle theta. Okay. All right. So if I want to talk about, because it doesn't matter what radius we're looking at, we tend to look at what we call our unit circle, the circle with our radius r, with radius equal to 1. Okay, so if my radius is 1, I can use that ordered pair. For now, if we just want to say that our radius is r, we can certainly do that. That would be the point r0, 0r, negative r0, and 0, negative r. Okay, so what if I wanted to know, for example, well, the first thing that I want to point out is, notice this corresponds with 90 degrees, 180 degrees, 270 degrees. Or we can think of that as pi over 2 pi, 3 pi over 2, etc. So what if I wanted to know the cosine of 180 degrees? Okay, well, it's my x value, which is negative r over the radius, so we get negative 1. What if I wanted to find the sine of 180 degrees? Well, the sine is my y value, which is 0 over r, which is 0. Okay. All right. Well, I claim then, if our radius is 1, this is going to give us our unit circle. So let's just take our radius to be 1. This is the ordered pair 1, 0, 0, 1, negative 1, 0, 0, negative 1. If I want to talk about, for example, the sine of 90 degrees, it's the ratio of my y value over my radius. Again, we're assuming our radius is 1. The sine of 90 degrees is always 1. The cosine of 90 degrees is my x value over my radius, and 0 divided by anything is 0. Okay. If I want to talk about so we've done our 90 degrees and our 180 degrees, and we can keep moving through these. We can talk about, for example, at 0 degrees. What is the sine of 0 degrees? Well, it's the ratio of my y value over my radius. It's 0. And the cosine is the ratio of my x value over my radius, which is 1. Notice my sine on my unit circle is consistently my y value, and the cosine is consistently my x value. Again, this gives us what we call our unit circle, which my hope is something that you've read about. These are pretty good things to know. I'm going to refer you at the end of this to page 370 in your book, because that gives you a lot of really important information. Okay, so if my sine of theta is y over r and my cosine of theta is x over r, I claim I can rewrite my x and y values in terms of these two functions. I can say that y is equal to r times my sine of theta, and x is equal to r times my cosine of theta. Okay, so this gives us a way, if we know our angle and our radius, to determine what our x and y value are. Now, what I want you to do is recall that if my circle is centered at 0, 0, then I have the equation for my circle, x squared plus y squared is equal to r squared. Okay, recall this goes back to section 5.1. Well, x is r times the cosine of theta. So we say r cosine theta squared. Y is the same as r sine theta. Okay, so now if I bring in my square, I have r squared cosine squared of theta plus r squared sine squared of theta equals r squared. I can divide this whole thing by r squared since it's in every term. And what we get is that the cosine squared of an angle plus the sine squared of an angle is equal to 1. This is called our Pythagorean identity. And this is probably, if you're only going to memorize one formula, pretty much everything else can be derived from this. This is the one to do. Okay, this is a really crucial relationship. Okay, so a couple of things that I want to note. Okay, suppose I tell you that the sine of some angle is 4/7. And I'm going to tell you that that angle is in quadrant 2. We want to find the cosine of that angle. All right, this is crucial. Okay, again, you always want to draw a picture. We know that our angle is in the second quadrant, and we're given that the sine is 4/7. Okay, so what we're going to do is we're going to draw a right angle going down here. And the sine, recall, is my y value. Okay. Okay, right? Y is my radius times my sine of theta. So how would we do this computation here? Well, here we go. Now, it might seem kind of funky because we're in a different quadrant. But what we can say is if we know that the sine is 4/7, we can plug this into our formula to find our cosine. Now, momentarily, I'm going to draw a picture and show you something called a reference angle, but I first need to define it. So first, what I'm going to do is just use this formula. We know cosine squared of theta plus the sine squared of theta is 1. So I can solve this for my cosine of theta. I have cosine squared of theta plus 16 over 49 is equal to 1. We can solve this for cosine squared of theta by moving the 16 over 49 over. Well, we know 49 49ths minus 16 49ths is equal to, well, 49 minus 16 is 33 over 49. And now we want just the cosine, so we take the square root. So I have the cosine of theta. You have to consider both your positive and your negative value. I can't simplify the square root of 33, but I can simplify the square root of 49. Now notice we got 2 possibilities, but we are told that we're in our second quadrant. Remember, your cosine is your x value. And in the second quadrant, our x values are negative. So our answer in this situation would be negative square root of 33 over 7. So what I want to do very quickly now is just emphasize about the signs of each of our trig functions in our quadrants. Okay. Here, x and y are greater than 0. Notice here, x is negative, y is positive. In our third quadrant, both our x value and our y value are negative. And here, x is positive and y is negative. Remember, if my sine has to do with my y value and my cosine has to do with my x value, then the sign, S-I-G-N, of the sine and cosine are going to be completely dependent upon that sign, S-I-G-N, of each of these values. In other words, in your first quadrant, both your sine and your cosine are always positive. In your second quadrant, your cosine is negative and your sine is positive. Here, both the sine and the cosine are negative because both x and y are negative. And in the fourth quadrant, your cosine is positive and your sine is negative. All right, so what if I ask you to find the quadrant? Which quadrant are we in if, how about I tell you that the sine is negative and the cosine is also negative? We would say that's quadrant 3. Okay. What about if my sine is positive and my cosine is negative? Well, which quadrant has a positive y value and a negative x value? That would be quadrant 2. Okay. So just like we talk about the initial side and the terminal side, if we want to talk about a point, we call it our terminal point. All right. So let's do another example. Another really common angle is 45 degrees. So I want to talk about that. Okay. Knowing your sine and your cosine of common angles is, again, one of those things you're going to learn just because we're going to be using them so often. Okay, so if I want to consider 45 degrees, which we know is pi over 4 radians, that's right about here. Okay, well, again, we can always just assume we're taking a circle of radius 1. Just because, again, the radius doesn't really matter. This is my y value. This is my x value. So we say xy. Now, one thing we know is that the cosine squared of that angle plus the sine squared of that angle is 1. Okay. Now, I'm deriving something. This is nothing you're going to have to do on your own. But notice, since this is a 45-degree angle, x has to be equal to y, simply because the 45 degrees divides my first quadrant in half. So if x is equal to y, then we can just say that this is going to be the same as that. So 2, let's just keep it in terms of cosine of 45 degrees. Again, I'm just using radians to get us used to these things, is equal to 1. I can solve this and say that the cosine squared of pi over 4 is 1/2. And then I take the square root of both sides. So I'm going to say that the cosine of pi over 4, or in other words, the cosine of 45 degrees is going to be equal to, we would get positive or negative root 2 over 2. How did I get that? Well, notice this is positive or negative, the square root of 1 over the square root of 2. The square root of 1 is 1. And then we have the square root of 2 in the denominator. Recall from an algebra class, we don't necessarily like to have radicals in our denominator, so we rationalize it by multiplying by root 2 over 2. And the square root of 2 times the square root of 2 is 2. Okay, so what this tells us is, in my first quadrant, the cosine of 45 degrees, we know cosine is positive, is root 2 over 2, as is the sine. Okay, now what if I told you now that my radius is equal to 5? Well, 5 times the cosine of pi over 4 is 5 times root 2 over 2. So we would say that's 5 root 2 over 2. Another way to show this, and actually the way that I prefer to look at it, is by talking about an isosceles triangle. Okay. If this side is length 1 and this side is length 1, we can get the length of the hypotenuse. Again, this is an isosceles triangle. These two lengths are the same. These two angles are the same using our Pythagorean theorem. And we get square root of 2 there. Okay. Notice that the sine is y over r, which is 1 over the square root of 2, which is root 2 over 2, as is the cosine. Now, suppose I wanted to take an equilateral triangle. Equilateral triangles are triangles where all 3 sides and all 3 angles are the same length or the same measure. In other words, each of these angles is 60 degrees. And let's just, for nice purposes, say that each of these sides is length 1. Okay. What I'm going to do now is draw a perpendicular bisector down from here. And I'm just going to hone in on this side. Okay. And in fact, I'm going to do that in my first quadrant. There he is. So I have that this is 60 degrees. Well, if that's a perpendicular bisector, we know this is 30 degrees, and that's 90. We have this is equal to 1. Well, notice we drew this perpendicular bisector down, which bisects this in half. This side is 1/2. And I know the length of this side squared plus the length of this side squared is equal to the length of that side squared. I'll call that y for obvious reasons. So let's find what this length is. We get y squared plus 1/2 squared is 1 squared. So y squared plus 1/4 is 1. Solve for y, you get y squared is 3/4. And take the square root, and you're going to get positive and negative root 3 over 2. All right. So there's a table on page 368 in your book and 370 in your book. Those are really, really important things. Okay. So the moral of the story, if we have all of these lengths, is that the sine of 60 degrees, that's y over r, is root 3 over 2. The cosine of 60 degrees is x over r. That's 1/2. Okay. Now, one of the things that you're going to see is we can do a very similar thing for a 30-degree angle. And you're going to see that the sine of 30 degrees is 1/2 And the cosine of 30 degrees is √3/2. Okay. And finally, from our previous page, we have that the sine of 45 degrees is the same as the cosine of 45 degrees since x is equal to y, and that's equal to √2/2. Now, this all works fine and dandy in our first quadrant. But in my initial example here, where I have the sine is 4/7, what do we do when we're in a different quadrant? Okay. Well, what you do is you find what we call your reference angle. Your reference angle is the size of the smallest angle from your terminal side to the horizontal axis. In other words, the x-axis. It's always between 0 and pi/2. All right. So what I want to do is just show you, okay, if we have a first quadrant angle, theta, okay, you can say that the sine is y/r, the cosine is x/r. What if we have a second quadrant angle and we want to find our sine and our cosine? Well, the way you go about doing this, and again, details given in your book, is you find the reference angle. Okay, we'll call that theta prime. That's the distance, that's the smallest angle from the terminal side to the horizontal axis. So if I wanted to know the sine of theta or the cosine of theta, what I would do is find the sine or cosine of the reference angle and then adjust the SIGN sign depending upon the quadrant. Okay. In my third quadrant angle, if this is my angle theta, this is my reference angle. And you draw that right triangle down. And finally, if you have a fourth quadrant angle, this is your reference angle. So going back to that earlier example, I told you that the sine of theta was 4/7 and we were in quadrant 2. Recall we used our Pythagorean identity to find the value, but we can also say, well, if the sine is 4/7, that's the value of y/r. Can we find this value here? Our x value? Notice we want to find the cosine of theta, which we know is x/r. Well, yes, we can use our Pythagorean theorem. I can say that 4 squared plus x squared is 7 squared. So 16 plus x squared is 49. Solve for x squared, you get 33. So we get the square root of 33. Notice I'm in my second quadrant, so this is negative. And if I now want to find the cosine of this, it's x/r, negative square root of 33/7, which I claim is exactly what we got there. So my point is this: if you want to find the sine or cosine of any angle, okay, what you do first is of theta. Find the reference angle, find the sine or cosine of your reference angle, and then adjust the SIGN, positive or negative, depending upon what quadrant that you are in. Okay. So I'm just going to go through maybe 4 or 5 examples, and hopefully that will help you. work through this. So suppose I tell you that the cosine of theta is 1/7, and I'm in my fourth quadrant. I want to find the sine of theta. Okay, again, lots of different ways we can do this. We can use sine squared plus cosine squared equals 1. Okay, totally legit. In fact, I'm not going to do it that way, but I would recommend you plug in 1/7 for the cosine and solve it for the sine here. You're going to see that you get the same answer. But I want us to think about using our reference angles. Okay, so we know that the cosine is 1/7. The cosine is x over r. So what I want to do now is I want to find my y value. Okay, Pythagorean theorem, my friends. 1 squared plus y squared is 7 squared. So I get that y squared is 48, and take the square root of that. Well, 48 is 16 times 3. I always want to simplify what I can. I'm going to get positive or negative 4 root 3. Notice I'm in my fourth quadrant. My y value is negative, so I get negative 4 root 3. So what is my sine of theta? It's y over r. Oh, excuse me, y over r. That's not r. So I get negative 4 root 3 over 7. And again, I claim if you would have plugged 1/7 in here and squared it and gone through the whole razzmatazz, you'd get the same thing. All right, so how about this? 225 degrees. What I want us to do is find our reference angle and then find the sine of those. Notice I'm in degrees here, so that's pretty cool. What quadrant is 225? Well, this is 180, this is 270 degrees, so I know I'm right here. I'm in my third quadrant, okay? So if this whole thing is 225 degrees, I want to find this angle here. This is my reference angle right here, okay? Well, this whole thing is 225 degrees. This portion is 180. So my reference angle is 45 degrees. Okay, this is going to be one of those angles that you know because 45 degrees, 30 degrees, and 60 degrees are just all over the place. We know that the sine of 45 is the same as the cosine of 45, and that's root 2 over 2. So remember, step 1, find your reference angle and find the sine and cosine of that reference angle. And now we adjust for the quadrant we're in. We know that both our x and our y values are negative here. So both of these are negative root 2 over 2. This may seem funky, totally takes a lot of practice. Okay, let's now do this with 300 degrees. Okay, where am I for 300 degrees? That's a fourth quadrant angle. Okay, well, we need to find our reference angle. That's right here, between the terminal side and the horizontal axis. So, well, if the whole circle is 360 degrees and we've gone 300, I claim that my reference angle here is 60 degrees. I know that my sine of 60 is root 3 over 2 and that the cosine of 60 is 1/2. Okay, at this point, you can just refer to your table in your book. But now that we found for our reference angles, we can now adjust the sine for our quadrant. The sine of 300 degrees Well, I know I got √3/2, but notice my sign is negative in my fourth quadrant because my y value is negative. And the cosine of 300 degrees, well, the cosine of 60 is 1/2. And since my cosine is my x value and that's positive in the fourth quadrant, I get positive 1/2. All righty. Let's do one more with degrees and then we're going to practice a couple with radians. What about 135 degrees? Well, what quadrant am I in? I claim 135 is definitely between 90 and 180. And if I want to find my reference angle here, well, this whole thing is 180. I want to subtract off this portion. Notice I get 45 degrees. I know that the sine and cosine of 45 degrees is √2/2. So to find the sine and cosine of each of those guys, well, I know I got √2/2 as the base for each of them. I just have to adjust the positive and the negative. My sine is positive in my second quadrant, so that stays the same. My cosine is negative in my second quadrant. All right, let's just do some now practicing in radians here. So what if I want us to find the sine and cosine, say, of 5π/4? Okay, first thing we need to do is figure out where are we? Well, we know this is pi, which is 4π/4. So I've just gone 1π/4 more. So this whole thing is 5π/4. This is my reference angle right here. Well, if this whole thing is 5π/4 and we want to subtract off this, I claim that my reference angle then is π/4. You're going to learn pretty quickly π/4 is the same as 45 degrees. And we know that the sine and cosine of π/4 is √2/2. Notice we're in our third quadrant. So for both of these, we're going to get negative √2/2 because both the sine and the cosine are negative in your third quadrant. All right, how about we do, let's see. How about 5π/3, sine and cosine of 5π/3? Okay, well, this is 3π/3. And because it's pi, this is 6π/3 because it's 2π. So we're just π/3 shy here. So I know that I'm in my fourth quadrant. This is 5π/3. Okay, and yes, this is 3π/2. If you wanted to get these in a common denominator, you would clearly have to put them in a denominator of 6, right? So this is 12π/6, this is 6π/6, and this is 9π/6. And notice here what we're looking at is 10π/6. Again, I just got a common denominator. So we're in our fourth quadrant. What is my reference angle? Well, this whole thing is 6π/3 minus 5π/3. My reference angle is π/3. Well, the sine of π/3, i.e. 60 degrees, is √3/2. And the cosine is 1/2. Now what we need to do is adjust for the SIGN of our quadrant. In other words, the sine of 5π/3, notice that's our y value and it's negative here. So I get negative √3/2. And the cosine of 5π/3 is going to be positive or negative 1/2. But in my fourth quadrant, my X value is positive. So I get positive 1/2. Again, I know this seems like a lot. It takes practice. Okay. So I just can't recommend it enough that you really, really just need to practice these things. All right, so now what I want us to do is just a few more examples just to reinforce this. So what if I want us to find an angle either between 0 and 360 or 0 and 2 pi that has the same sine value? As, say, pi over 3. Okay, well, sine of pi over 3 we know is root 3 over 2. Okay, all I'm asking for is, well, notice my sine is positive. Sine of pi over 3 is positive. What other quadrant is my sine positive? In the second quadrant. In other words, we want to find this angle that has a reference angle of pi over 3. Well, again, this whole thing is pi. So 3 pi over 3 minus 1 pi over 3. 2 pi over 3. Okay. Let's practice another one. What if I want us to look at, say, 140 degrees? I don't know what the sine of 140 degrees is off the top of my head, but I know it's in my second quadrant. Well, it's going to be the same as my reference angle. If this whole thing is 180 and this is 40 degrees, then 40 degrees is going to have the same sine value. Now let's bop to another quadrant here. What if I want us to look at, say, 4 pi over 3? Okay. Well, where is 4 pi over 3? That's in my third quadrant, 3 pi over 3. Okay. So what I'm going to want to do is find another angle here that has the same sine value. Well, in other words, it has to have the same reference angle. My reference angle here is going to be pi over 3. Notice my sine is negative here. What other quadrant has a negative sine? My fourth quadrant. So essentially what we're wanting to do is find a fourth quadrant angle that also has a reference angle of pi over 3. This whole thing is 6 pi over 3 minus pi over 3. So we would get 5 pi over 3. Again, we're just playing with the reference angles. So let's do that again, but now let's do that with our cosine. So we want to find an angle that has the same cosine value. Let's do, how about 80 degrees? Okay. 80, and again, we're talking about our cosine. Key thing to remember is cosine's positive in both of those guys and negative in both of those guys. So here's our 80 degrees. Well, in what other quadrant is our cosine positive? Down here. So what angle do we have that has a reference angle of 80 degrees? Well, whole thing is 360 minus 80 So the cosine of 280 degrees is going to be the same. What if I want to find an angle? How about 4 pi over 3? Again, cosine is positive, positive, negative, negative. We know 4 pi over 3 is here. Okay, look at your reference angle. That's all we care about. If this whole thing is 4 pi over 3 and pi is 3 pi over 3, we have a reference angle of pi over 3. What other quadrant has a negative cosine value? My second quadrant. Okay, so what second quadrant angle has the same reference angle? I claim 2 pi over 3. So we know that the cosine of 4 pi over 3 is exactly the same as the cosine of 2 pi over 3. All righty, let's just do one more with degrees just so that we're getting the hang of it. I want to find another angle that has the same cosine value, say, as 305 degrees. Well, 305 degrees is in my fourth quadrant. What is my reference angle? I claim it's 55 degrees. Cosine is positive here. What other quadrant has a positive cosine? My first quadrant. Therefore, it's going to be 55 degrees. All right, again, I can't emphasize enough, you want to play like crazy with these things, okay? I know it takes a while, but once you get the practice, you'll see that it's the same routine. All righty.